Welcome back to Honors Calculus. In this video, we're going to be using implicit differentiation. We've talked previously about how to differentiate a function implicitly, how to find an expression for y prime when it doesn't look like y is a function of x. I mentioned in that video that we could then use that and continue on as we have before, and I want to show you exactly what I mean in this video. So without further ado, let me get my head out of the way and let's take a look at a particular problem. Let's take a look at x squared over 9 minus y squared over 25 is equal to 1. This equation is the equation of a hyperbola. Again, if you aren't comfortable with how to graph a hyperbola offhand, that's fine. That's not a big deal. You can, of course, use computer software to graph this if you so desire. But a hyperbola is one that has some auxiliary equations. It's x squared over 9. Square root of 9 is 3 or negative 3. It's y squared over 25. Square root of 25 is 5 or negative 5. And then the usual procedure is to draw a rectangle containing those and then draw some lines that go through the rectangles at diagonals. In this case, x is positive, y is negative. So we take the x-intercepts of the box, we put down points, and we draw some curves that go to the diagonals as asymptotes. And that's what the graph of this thing is going to look like, more or less. You can use computer software to get a nicer graph if you so desire, but having this is good enough for me. We'll be doing a couple of things with this curve, but for right now, I want to start by finding the equation of the line tangent to the curve at the point negative 5, 20 over 3. Negative 5, 20 over 3 is right about there. So that gives us a picture of what we're looking at. We can see that we're getting pretty close to the asymptote already in how I've graphed. We have a rough idea that it should look something like that. And we can figure out slope and so on from there if we so desire. But the first thing I always suggest when we're looking at finding the equation of a line tangent to a curve at a point is make sure that that point is actually on the line. Make sure that no one has done anything stupid up until this point. I'm writing these problems. I guarantee you that it's possible for someone to do something stupid before they give you the problem. But we plug in x is negative 5 and y is 20 over 3. Negative 5 squared is positive 25. Uh, 20 over 3, the whole thing squared. Well, that's a 20 in the numerator. 20 squared is 400. And then the denominator will have 25 times 3 squared, which is 9. And sure, I could multiply 25 times 9. I probably will a little bit later on, but writing it like this is convenient because it shows off. I'm going to have to multiply this fraction top and bottom by 25 in order to get everything to work. And 25 times 25 is 625. 25 times 8 is 200. So 25 times 9 is going to be 225. What do you know? 625 minus 200 is 225. And 225 over 225 is equal to 1. All right, so we know that this point actually is a point on the curve. That's useful to know, definitely valuable to us. But again, that's just checking to make sure that everything is working, so it's technically not part of the problem. We're asked to find the equation of the tangent line. So let me bring that original equation back here. And remind you that in order to find the equation of a tangent line, we need the derivative. This is an implicitly defined function, which means we're going to differentiate implicitly. Differentiating with respect to x, the derivative of x squared over 9 is going to be 2x over 9. The derivative of y squared over 25 is going to be 2y over 25. Then using the chain rule, remember we're differentiating with respect to x, so we need the derivative of y with respect to x, which is y prime. And on the right-hand side, the derivative of 1 with respect to x is 0. Rearranging this equation, multiply by 25, divide by 2y. So we get 2x times 25 is equal to 9 times 2y. And that's going to be equal to y prime. Hey, there's some 2's that are going to cancel each other out. And we're left with 25x over 9y is equal to y prime. All right, that's useful, but we're not done. Because remember, this problem asked us to find the equation of the tangent line. So now that we have that, let's go back. Remember that our point is -5, 20 over 3. So we get 25 times -5 over 9 times 20 over 3. 25 times -5 is -125. 9 times 20 over 3. Well, conveniently, 9 over 3 is 3. 3 times 20 is 60. So we've got -125 over 60. I guess we can try to reduce this fraction. They're both divisible by 5, giving me 25 over 12. I don't think it's going to reduce any further, so there is our slope, -25 over 12. Then from that, y minus the y coordinate we care about is equal to our slope times x minus the x coordinate we care about. And technically we're done, but let's clean up a little bit. All right, 20 over 3 is the same thing as 80 over 12. -125 plus 80 is -45. And 45 and 12 are both divisible by 3. So that's going to be 15 over 4. I lost my x writing that last step down. Sorry about that. All right, there we go. We were able to write the equation of the line tangent to the curve at the point in question. But since we're differentiating, it stands to reason we can probably take multiple derivatives if I want to find y double prime. Once again, it seems a lot scarier than it actually is going to be, although I'll be honest, this isn't going to be a lot of fun. Remember, y double prime, by definition, is the derivative with respect to x of y prime. And of course, we know that y prime is 25x over 9y for this particular problem. So we want to take the derivative with respect to x of 25x over 9y. That's a fraction. We're going to have to use the quotient rule. Derivative of the numerator times the denominator minus the numerator times the derivative of the denominator. Derivative of 9y is 9, then chain rule derivative of y is y prime, all over denominator squared. Clean up a little bit. 25 times 9, we've said before, is 225. Although I guess that we have 225 in the numerator, we have 81 in the denominator, 9s will cancel out there. And this is actually 25y minus 25x y prime all over 9y squared. But wait a second, I know what y prime is. It's 25x over 9y. Now I've got a fraction with fractions in it, so multiply top and bottom of the big fraction by 9y. 25y times 9y is 225y squared. 25x times 25x divided by 9y times 9y will cancel each other out. We'll get 625x squared all over 81y cubed. Right. I said it wasn't going to be fun. I didn't say it was going to be difficult. And I think that's fair for this. Right? We got through it. We were able to find the second derivative. It was messy, but we were able to. Right? It's nothing new. It's nothing different. It feels scary. It feels like it's something different because we have these y's in the middle of the expression, which means we're differentiating again implicitly, but everything worked out fine. All right, so there's a couple of things that we can do with implicit differentiation. There are more. There are some very practical applications that we'll be looking at, but for this video, this idea is good enough. So let me get my head out of the way, and we'll wrap up with one more for you to try. I would like you to find the equation of the line tangent to the curve xy minus y squared equals 0 at the point 1, 1. All right, take a few minutes playing around with this one, see what you come up with there, and I'll see you in the next video.